Hi, this is trimester 2, day 17, related rates 3. We need to start today with a little bit of a geometry review, and we want to remember that if I have two triangles where angle A, angle B, angle C, angle big B, A, big B, and big C, if angle A is equal to angle big A, if angle little b is equal to angle big B, and if angle C is equal to angle big C, then we can say that these triangles are similar and their sides are in proportion. That is that AB is to AB as little bc is to big BC and little AC is to big AC. So that's just a review from geometry. We're going to come back. We're going to need to use that in this problem. So in this problem, it's another related rates problem. We're going to organize it the same way we did before with our what do we always know, what is it we're trying to find, and when, our always equation and derivative, and then look at what's happening at this moment. So in this case, we have Kathy, who is 5 feet 9 inches tall. Here's Kathy. She's 5 feet 9 inches tall. And she is walking toward a 23-foot tall lamppost. And she's at a rate of 5 feet per second. So she's walking toward that street post at 5 feet per second. We want to know how fast is her shadow shrinking when she is 9 feet from the lamp and then at 12 feet from the lamp. So we need to get some definition here, defining our variables so we know what's going on. Well, if this is a street light with light coming off of it, we know that it's going to cast a light down towards Kathy, and her shadow is going to be out here. So we might want to call this distance from Kathy to the street light X. We know that this is 23 feet tall, and that's not changing. We'll call that Y. And we'll call this length of the shadow A. You might want to use an S. I never do because my S's always look like 5s. This 5 feet 9 inches is problematic because everything else is in feet, and to have this other unit of inches becomes an issue. So let's change that so that we have it just in feet, and that would be 5.75 feet. Do that quick conversion. So we want to know how fast is her shadow shrinking. We're looking at a rate of change, and that rate of change is how A is changing over time. So what we're trying to find is dA dt when, and for this first problem, when she is 9 feet from the lamp, when x equals 9. So we need an equation, back to what we did yesterday. We need an equation that's going to combine all of the information we're looking for. And while the Pythagorean theorem is good, it's great, it is not a way for us to take all of these pieces and put into a single equation. So that's where we're going to go back to that geometry review we have. And we're going to say that if we take Kathy's height relative to the length of the shadow, so Kathy's height is to the shadow as the street light is to the entire distance, we have a triangle that is Kathy and the shadow, and we have shadow, distance to light, and the light being the larger triangle. It's similar to this triangle. We know that this angle is the same as this angle. We know that this angle is the same as this angle, which means that that angle, and which would mean that that angle has to be the same as that angle. So they are similar triangles. We can then say that Kathy's height, the 5.75, is to the length of the shadow, as the 23 is to the entire length. And then by cross multiplying, we have 5.75 times a plus x is equal to 23a. We know we're going to need to take a derivative. And at this point, I don't really like that form of the derivative. It's kind of messy. So I'm going to go ahead and tidy up this equation by distributing 5.75a plus 5.75x is equal to 23a. I'll get my a terms together. I'll subtract the 5.75a from each side. So I have 5.75x is equal to 17.25a. And now I'm in a place where I can take the derivative. 5.75 dx dt is equal to 17.25 dA dt. So I've taken the derivative. I'm trying to find dA dt, so I'm going to divide by that 17.25. dA dt is equal to 5.75 divided by 17.25 dx dt, or dA dt is equal to 1/3 of dx dt. The thing we want to take note of here is that our x value doesn't come into play at all. Our dA dt is simply determined by 1/3 of our dx dt. So when we go to plug in, go to that next box, that red box, we can see that dA dt is equal to 1/3 of -5. Well, now why is this negative? It's negative because if this is our dx dt, the rate at which she's walking toward the streetlight, x is getting smaller. So dx dt is a negative value. So dx dt is -5 feet per second, which gives us -1 2/3 feet per second. And that's for any x value. It doesn't matter whether x is 9 or x is 12 or x is whatever you'd like to plug in. That dA dt is still going to be -1 2/3 feet per second. So this, what appeared to be a two-part problem, in fact was only a one-part problem. But we did need to have this review of geometry. You're going to want to have that for homework tonight. Remember, just have a look back at that. So our second problem, it's kind of nice because it looks like it's going to be a challenging problem. The challenging part is drawing a three-dimensional drawing. A rectangular pool 20 feet deep with a base of 10 by 12 feet is being filled with water at a rate of 20 cubic feet per hour. At what rate is the water level rising? Well, so it's kind of a strange shaped pool. It's 10 feet by 12 feet by 20 feet deep. So I'll do my best to draw this. Okay, so this is 10 feet, this is 12 feet, and this is 20 feet. So for each of these, this is, we're going to assume a concrete pool or some rigid pool. Those values aren't changing, but what is changing is the height of our water. We've got water filling up this pool, and it is at some height, and that's going to be changing because we're adding water to the pool. So this height of the water, we might want to call that H. H for the height of the water. Okay, and that part is changing. The other thing that isn't changing is they say that it's being filled at a rate of 20 cubic feet per hour. So what is changing here? It's the volume of the water that's changing. the volume is changing. So our dV dt is equal to 20 cubic feet per hour. Okay, and again, that's not changing. Well, what is it we want to find here? At what rate is the water level rising? So it looks like we're trying to find dH dt all the time. Not when h is some specific thing or when or at a given anything. It's just always, when, always. Or I guess we could say when h is between, it's greater than 0 and less than 20. If the pool starts out empty and you're putting in water until it gets to be 20 feet deep. So an equation. Well, we're interested in dH, so we know we have to have an h in our equation. We're given a dV dt, a volume, information about the volume, so it seems reasonable to be looking for a volume equation. So this is a rectangular prism. The volume of a box is the base times the height times the depth, or length times width times height. Well, in this case, the volume, our base, is 10 by 12 by, and now the height, we're tempted to put in this 20, but what we're interested in is the height of the water. So that's where the h is going to go in. As I say, it's tempting to put that 20 in there, but that would give us the volume of the entire pool if it was full of water up to the top. But we're looking at the water being filled, so the water isn't up to the top yet. So V is equal to 120H. We can go ahead and take our derivative here, that dV dt is equal to 120 dH dt. And at this point, we can go ahead and put in that dV dt that we know to be 20 equals 120 dH dt. So dH dt is equal to 20 over 120, 1/6 foot per hour. Okay, so that's all I've got for notes today. The new things that you need to take away from today are the review of geometry, and then also that we need to continue to look at what are we doing for equations. That oftentimes the hardest part, one of the harder parts, is picking out the equation we're going to use and deciding where does that come from. Okay, so good luck, and